In the previous video, we learned what the nth root of unity is and what the primitive nth root of unity is. In this video, I'll show you two useful properties of an nth root of unity that we're going to need to understand the FFT. The two useful properties of a primitive nth root of unity is that w raised to the power by is equal to w raised to the power by mod n. And the second useful property is that under certain conditions, w raised to the power of n divided by 2 is equal to minus 1, and minus w raised to the power by is equal to w raised to the power of n divided by 2 plus I. So let's see why these two properties are true. Let's start with the first one. W raised to the power by is equal to w raised to the power of I mod n. We'll begin by writing this integer I as a multiple of n plus some remainder. So now we can say that wi is equal to w raised to the power of k multiplied by n plus j. This is equal to w raised to the power of k multiplied by n times w raised to the power of j. Now w is a primitive nth root of unity, which means that w raised to the power of n is equal to 1. So let's go back over here. We can simplify this expression as swap the orders around. To make it clearer, we can put this in a parentheses. Remember, w is a primitive nth root of unity, so w raised to the power of n is equal to 1. This expression inside the parentheses is equal to 1. Now, what is 1 raised to the power of k, to any power of k? Well, this is 1 to the k, which is equal to 1. So this part is equal to 1. And then we still need to multiply by w raised to the power of j. Okay, so this is what we have so far. W raised to the power of I is equal to w raised to the power of j when I is equal to k multiplied by n plus j for some k and j. And here, since we're writing I as a multiple of n plus some remainder j, I'll make it clear that j will be a number between 0 and less than n. Okay, how about I mod n? What is this equal to? I mod n, by definition, is equal to the remainder j after we find the largest number that is a multiple of n less than or equal to I. So this is simply equal to j. Okay, now we can put all of these green boxes into a single statement. So starting with wi, we know that this is equal to wj. But from this equation, we know that j is equal to I mod n. So now we have our final equality, that wi is equal to w raised to the power of I mod n. What this statement really says is that w raised to the power of I wraps around after multiples of n. Okay, that's the first useful property. Let's move on to the next useful property of a primitive nth root of unity. That is, w raised to the power of n divided by 2 is equal to minus 1 under certain conditions. I'm going to first explain the condition when this is true. This condition is true when 2 divides n, in other words, when n is a multiple of 2, and when the primitive nth root of unity is in a prime field that's called as f of q. As a quick review, what it means for w to be inside a prime field f of q is that w is 1 of 1 to up to q minus 1, and here we're doing multiplication and addition mod q, where q is a prime number. Under these two conditions, you'll have the w raised to the power of n divided by 2 is equal to minus 1. And from this fact, you can deduce that minus w raised to the power by is equal to w raised to the power of n divided by 2 plus I. To see this, note that minus w raised to the power by is equal to minus 1 multiplied by wi. Since minus I is equal to w raised to the power of n divided by 2, then minus 1 multiplied by wi will be equal to w raised to the power of n divided by 2 plus I. So now let me explain why this is true. Since w is a primitive nth root of unity, w raised to the power of n is equal to 1. We can restate it as w raised to the power of n minus 1 is equal to 0. Since in this condition n is a multiple of 2, we can rewrite w raised to the power of n minus 1 into two parts. W raised to the power of n divided by 2 plus 1 and w raised to the power of n divided by 2 minus 1. You can check for yourself that when you multiply and then add and then simplify everything, these two equations are the same. Since here we're working with prime fields, you also need to check that this is an integer, which is the case since 2 divides n. So we have n divided by 2 is an integer, and this equation also holds. Moving on, since w raised to the power of n minus 1 is equal to 0, this expression is also equal to 0. Next, we're going to analyze these two individual expressions and deduce that this part is equal to 0. But before we do that, let's make sure that it's impossible to multiply two non-zero numbers that results in 0. Now recall that this multiplication and addition, we're doing this mod q, where q is a prime number. So this equation is actually saying that multiplying these two expressions is equal to q, where q is a prime number. Now, since q is a prime number, it's impossible to find two numbers that are less than q that when we multiply is equal to q, since q is a prime number. So let's summarize what we have found out so far. Q is prime, so it's impossible for this side to not equal to 0 and this side to not equal to 0. And it happens that when we multiply two non-zero numbers, it equals q, which is equivalent to 0 mod q. So for this condition to be true, we cannot have that both of these expressions are non-zero numbers. One of them has to be equal to 0. Either the left term is equal to 0 or the right term is equal to 0. So let's try to find out which expression is equal to 0. We'll start with this one. What does it mean for this part to be equal to 0? Well, if this was the case, then we can rearrange the equation to say that w raised to the power of n divided by 2 is equal to 1. But remember, w is a primitive nth root of unity, which means that w raised to the power of n is equal to 1, and w raised to the power of I for I less than n is not equal to 1. In our case, w raised to the power of n divided by 2, which is less than n, cannot be equal to 1. So this cannot be true, since w is a primitive nth root of unity. W raised to the power of n divided by 2 minus 1 cannot be equal to 0. So it must be the case that this part is equal to 0. Okay, so what does it mean for w raised to the power of n divided by 2 plus 1 to be equal to 0? We can rearrange this to say that w raised to the power of n divided by 2 is equal to minus 1. And that completes the proof for why w raised to the power of n divided by 2 is equal to minus 1 under this condition, when n is a multiple of 2 and when the primitive nth root of unity is inside the prime field f of q. These are two useful equations to remember to understand FFT.